Right, today we're going to look at how a light-dependent resistor works in a light sensing circuit. So this is the light-dependent resistor. A simple circuit with a 9-volt battery connect up positive angle to the light-dependent resistor. Basically, this is a resistor. The resistance of this resistor change with the brightness of the environment. We're going to look at it in a minute. And this light-dependent resistor is connected to the LED and then go back to the negative terminal, and it is a complete loop. So it is a circuit, right? It's a circuit that should work. I start a simulation and see how it goes. Nothing happened. I click on that because this light-dependent resistance is responding to the brightness of the environment. TinkerCAD allows us to control the brightness of the environment. So when it's here, it's completely dark, and when it shifts up, the resistance drop, right? So this circuit is working, but we want to know how does it work. So I have two multimeter here set up on the desktop. One is configured as a ohm meter. This measures the resistance. You can see a little R here, and this one is set up as a voltmeter to measure the voltage. I'm going to connect it up to measure the voltage across the LED. Before we do that, I would like to know how the resistance of this LDR change with the brightness of the environment. So I turn off this simulation for a while. I want to get another LDR and do a measurement here instead of pulling it out from the circuit. I don't need to. So I just get a LDR, I have light dependent. All right, you found that light dependent a photoresistor show up. This is another name for a light-dependent resistor. So for TinkerCAD, it's pretty smart that it knows other name for the same component. So I want to connect it here directly to the ohm meter to measure the resistance. So the easiest way is to rotate it and then connect it here. All right. So now I run the simulation, and then I click that. Is that when this LDR is in a very dark environment, the resistance 180 kilo ohm, which is pretty high, and that's why the LED is off. When it's dark, when I shift it to the very bright environment, the resistance dropped to 506, which is a pretty good resistance for a LED circuit, which is just right for it. So the resistance of a LDR can change with different product. Different manufacturer have different specification. Some of them are higher. The resistance, the range of resistance changes could be wider. Some of them are narrower. It really depends on the product. Right now, if I want to know what happened in this circuit when the brightness of this LDR change, how does it affect the LED? That's something I would like to know a bit more. So I'm going to connect a voltmeter across the LED and see what happened. Let's stop this one. I'm going to connect a voltmeter. So this side is a negative. So I'm going to connect this one here. but the positive is kind of crossing it. It doesn't really matter, you can cross it, right? It's not a problem to cross it. All right, so this is a blank one, and I would like to make it neat and tidy. And the red one, I need to connect here. I can just draw a line here to directly to this point. It's okay to do it that way. All right, so red. All right, so crossing the two lines, it doesn't cause any problem because they are not connected. So these two Y are not connected, but just cross over. All right, now I can run a simulation, start simulation, and now this I can see the voltage across this LED. A LED normally take about 2 volt for this red LED, take about 2 volts to turn on. And so far, even if the LDR is in a completely dark environment, there's still current flowing through this circuit. The current is just too low to turn on the LED. So when I increase the brightness of the environment, you can see the voltage increase. And the LED start to turn on, right? You can see the LED start to turn on and until it's full brightness. And yeah, it's about, in this particular case, the LED is 2.02 volt, which is about its full brightness. If we want to know the current through this circuit, we can do that. We can connect an ammeter to see the actual current flowing through this circuit. Yeah, we can just try it. Let's stop it first. I'm going to add a, okay, I don't need it. I could just turn this one into a ammeter. So let me see, how should I do that? Okay, I could just do it here. Turn it to a, okay, this way. I'm going to change it. Instead of measuring resistance, I'm going to change it to measure amperage. Right, so to measure current, I need to remove this one. And then one end connect to the positive end of the ammeter. That's what I need to do. All right. Okay. You can always adjust it a little bit to make it look tidy. Right, okay, shouldn't be red because it's a connection. Normally I just pick green for the connection which is not the positive or negative. And the other end of this emitter go to the negative terminal. So I need to connect it here. All right, this time I choose black because it's connected to the negative terminal. All right, now I have an ammeter to measure the current. I run simulation again and click on the brightness control. Now you can see when it's completely dark, the current flowing through this circuit is 40 microamp, which is very small. Now if I start to increase the brightness of the environment, it just go to 2 milliamp and then keep going up. 6 milliamp, 7, 8, 9, 10. Okay, the maximum is about 13, 14 milliamp, which is still below the maximum acceptable current. For a red LED like that, it can take up to 20 milliamp without damaging it, and it probably is full brightness. So in this circuit, it's not at its full brightness yet. Right, we just stop here. See you next time.